EES, which is pronounced EASE, is an acronym for Engineering Equation Solver. EASE is an engineering tool, and therefore the variables that you use in EASE typically represent physical quantities, and these are often measured quantities. So we've seen how these variables can be assigned values and units, and in the previous video in this section we saw that EASE variables can also be assigned some uncertainty. The results of calculations that involve measured variables therefore will also have some uncertainty, and that uncertainty can be determined using EASE's built-in uncertainty propagation feature. In this video we'll do another example using uncertainty, and we'll look at a few additional features that are related to uncertainty analysis in EASE. In the next video we'll show how to transition these concepts most effectively into the analysis of a set of data. Let's consider an example where the heat transfer coefficient associated with the internal flow of fluid through a duct is being measured. The duct has an unconventional cross-section, but its cross-sectional area for flow and its perimeter are both measured. The length of the duct is also measured, and the wall temperature is controlled to be as uniform as possible, and its value is measured at 3 locations. The inlet and exit bulk temperature of the water pumped through the duct is measured using redundant temperature sensors. The flow rate of the water, the inlet pressure, and the pressure drop across the duct are also measured. These measurements, together with their uncertainty, are summarized in this table, and they can be used to determine the heat transfer coefficient, as well as the Reynolds number, and the average Nusselt number, and the friction factor, and the uncertainty in these calculated quantities. So here we'll calculate these quantities, and then we'll use EASE's uncertainty propagation feature to determine the uncertainty in these quantities. The measured quantities are entered into EASE here, with the redundant temperature measurements being placed into arrays and all of the units being converted to base SI units. The redundant temperature measurements are averaged in order to determine the average wall, inlet, and outlet temperatures. The properties of water are computed using the average of the inlet and outlet bulk temperatures and the average pressure. The mass flow rate and the bulk velocity are computed, and then the effectiveness is computed from the temperatures, and the number of transfer units is calculated using the appropriate effectiveness NTU solution. Finally, the conductance is obtained and divided by the area in order to get the heat transfer coefficient. The dimensionless parameters are computed here. The characteristic length for this problem is the hydraulic diameter, and that's used to determine the Reynolds number, the Nusselt number, and the friction factor. And solving now leads to the results that are shown here. The uncertainties in the measured quantities are entered here, and they're assigned to variables. This makes it easy to change their values later if I want to analyze parametrically the effect of some uncertainty on a result. And note that each of the individual temperature measurements has the same uncertainty. In order to carry out an uncertainty propagation study, it's necessary to select uncertainty propagation from the calculate menu. Here in this window we need to specify the calculated variables, and these are basically those variables that we want to know the uncertainty of. And for this problem that would include things like the heat transfer coefficient, as well as the Reynolds number, Nusselt number, and friction factor. And then we also have to select the measured variables. So these are things like area, for this problem also perimeter, length, inlet pressure, pressure drop, flow rate, and then all of the temperatures. In the professional version of EASE, array variables can be selected to be among the measured variables in an uncertainty analysis. And so if I uncheck the expand array button as shown here, I can select the entire array Tin, for example, and that will then expand that array into its elements and select all of the elements. So we'll do the same thing here for Tout and for Twall. And then finally we'll select the Set Uncertainties button, and that brings us to this window, which allows us to set the values of the uncertainty for all of those measured variables. So we're going to use those variables to set the uncertainties, as I'm doing here. Note that all of the elements of the temperature arrays have the same uncertainty, so I will deselect the Expand Arrays button, or checkbox, in order to collapse the arrays, and then I'll set the uncertainty of all of the elements at once to the variable U sub t. Once I'm satisfied that the uncertainties are all set, I can select OK, and then OK again to initiate the calculations, as well as the accompanying uncertainty propagation calculations. and the results are shown here. So I have a solution window, and then I have this window showing the uncertainty results. EASE is going to report the uncertainty in each of the calculated variables that I selected, and it's also going to report how this uncertainty depends on each of the measured variables. So for each measured variable, it's possible to see here the partial derivative of the calculated variable with respect to that measured variable. So this is basically telling you how sensitive the calculated variable is to the measured variable. And the product of this partial derivative with the uncertainty in the measured variable is then the uncertainty that can be attributed to that particular measured variable in the calculated variable. The percent of the total uncertainty that can be attributed to each measured variable is also reported over here. For those measured variables that have alternate units defined, it is possible to set their uncertainty values in those alternate units. So for example, here I can set an alternate unit of millimeters squared for cross-sectional area, which is the variable AC. And then when I return to the uncertainty propagation window and set the uncertainty values, you can see that now it's possible to select between the primary and the alternate units when I specify the uncertainty in AC. So I can change the uncertainty value here from the value in meters squared to the value that's in millimeters squared, and then run the propagation calculations again. There are some additional features in EASE, functions that you can access that allow you to get a hold of these results from the uncertainty propagation calculations within the equations window itself. And these are really useful if you'd like to do some calculations that actually involve the uncertainties. So the uncertainty of function returns the assigned or calculated uncertainty of the variable that is provided as the argument to this function. So for example, if I type the command here, UHTC is the uncertainty of HTC, and then when I solve, I'll see that the value of UHTC is the calculated uncertainty of the heat transfer coefficient, which for this problem is 303.5 watts per meter squared Kelvin. And I can use this result then to calculate things like what is the percent uncertainty in the heat transfer coefficient, which I'm doing here. And that leads to a percent uncertainty of about 1.56%. So note that the value returned by the uncertainty of function is going to be 0 if you initiate the calculations without using the uncertainty propagation command. So if I just use calculate, I'll get 0 because it didn't actually do the calculation of the uncertainties. If I do uncertainty propagation, then I'll get the actual uncertainty. The uncert.percent command returns the percent of the uncertainty for the calculated variable that can be attributed to one of the measured variables. So it requires two inputs, where the first one is the calculated variable and the second is the name of the measured variable. So for example, this command will return the percent of the uncertainty in the heat transfer coefficient that can be attributed to one of the wall temperature measurements, which ends up being about 7.4%. It's not possible to use this function except when you're using the uncertainty propagation command. The uncert.pardiff function returns the calculated partial derivative of a calculated variable with respect to a measured variable. So the command here is going to return the partial derivative of the heat transfer coefficient with respect to one of the wall temperature measurements. So this would be a quantity that has units of watts per meter squared Kelvin per Kelvin, right? So it's the partial derivative of heat transfer coefficient with respect to temperature. When you multiply that partial derivative by the uncertainty in the wall temperature, it's going to provide the uncertainty in the heat transfer coefficient that can be attributed to this wall temperature measurement. Okay? When we do this calculation, it ends up being about 82 watts per meter squared Kelvin of uncertainty in the heat transfer coefficient that is related to that measurement of the wall temperature. Note that because of how the uncertainties are combined using the root sum square method, this value of 82 is not 7.4% of the total value of 303.5 watts per meter squared Kelvin, which is the total uncertainty in the heat transfer coefficient. Rather, the way to think about it is that if this uncertainty in the wall temperature were not present, if that 82 were not present in that calculation, the total uncertainty would go down by about 7.4%. In our next video, we'll look at how to carry out uncertainty calculations on a set of data that is contained in a table. So this is one of a series of tutorials that is meant to describe the operation of the Ease software. If you want to get more information about Ease, or obtain the software, or access more of these tutorials, please go to the website fchartsoftware.com. These tutorials are excerpted from the book Mastering Ease, which can also be obtained from this website.